Hi, welcome to Advanced Math, Unit 12, Vectors, Part D, page 2. Now, we said at the beginning of this section that we were going to be somehow connecting vectors, lines, and planes, and so we're going to get into that right now. So this is sort of a puzzle, and I'll walk you through it because some people get confused by what we're talking about. So write an equation for a line in standard form. So that's the ax plus by equals c, and use any specific numbers. I'm just going to use some random sample numbers for a, b, and c, and I'm going to choose the ones that are on our written answer key, but um, you could choose any other, and I would choose integers, but anything should work. So like 2, 3, and 4. So we'll write the values of a, b, and c. So this equation for this line is 2x plus 3y equals 4, and that means these coefficients a, b, and c are 2, 3, and 4. We're not getting too devious here, I think. Now, thinking about the equation for this line, 2x plus 3y equals 4, what I want you to do is find any 2 points that you know are going to be on the line. So any 2 x and y combinations that will make that equation work. And we're going to name those points P and Q. And so the points that I came up with for this are the points 2, 0, and -1, 2. And you can think for yourself, if I plug these numbers, this x and y in for x and y in this equation, will it work? Yep. P will be 4 equals 4, and Q would be -2 plus 6 is equal to 4, and that definitely works as well. So there's an infinite number of possibilities. These are just 2 that I happen to have chosen. Now, we want to use these 2 points to create a vector from P to Q. So you might remember when you're doing a vector from P to Q, you take the coordinates of Q and subtract the coordinates of P. So the x-coordinate of Q is -1, and if I subtract the x-coordinate for P, I'm going to get -3. So the first component of this vector PQ is going to be -3. And if I subtract 0, which is the y-coordinate for P, from 2, the y-coordinate for Q, I'm going to get 2. So a vector, I'll sketch it over here, that connects P to Q, that would be vector PQ, has the components -3, 2. And that's a vector, and those points are chosen to be on this line. So that's a vector that's parallel to the line that passes through P and Q. So P and Q were chosen by me so that they'd lie on this line. That's the line that I defined up here. And from those 2 points that I chose, I also defined a vector that would connect the two of them. Now, vectors, as I've said before, don't have any particular location in space. They just have a direction and a length. Okay, so that makes some sense. Now, let's move this up a little bit. We're going to learn a little mathematical parlor trick that you could use to wow your friends and family. We're going to create a vector, u, whose components are equal to the values of a and b in the original linear equation. So if you go back up to the top of the page and look at that linear equation that I wrote, a was 2 and b was 3. So remember, these are the coefficients in the linear equation. These aren't points on the linear equation. This isn't a vector on the linear equation. These are just the coefficients of a and b of a linear equation in standard form. So now, this is kind of arbitrary. I've created a vector, u, from those coefficients in the linear equation. And now we're just going to try something. We're going to take this vector and we're going to take its dot product with PQ to see what we get. So u dot product with PQ is going to be this product. And that, if I take the x components and multiply them, it's going to be -6 plus 6 equals 0. So the dot product of vector u and PQ is 0. Now, I chose 2 random points on the line. And it turns out, I'm not proving this, but we could prove it. It just turns out that when you do this, if you take the coefficients in the linear equation and form a vector from them, and you take the a vector that is known to be parallel to the line and take the dot product, you're going to be 0, which means that this vector u is perpendicular to this vector PQ, which is parallel to the line. In other words, the vector formed from the coefficients a and b is perpendicular to the line itself. That's what this is actually trying to say. Because remember, PQ is a vector that's parallel to the line. And by taking this dot product and getting 0, I know that this vector that's parallel to the line is perpendicular to this vector that I created from the coefficients. And that is a cool and powerful idea.